Hi everyone, it's great to be talking to you all. My name is Alex Woodfinden. I am a third year PhD candidate at the Worsley Centre for Astrophysics, and today I'm going to be talking about geometry and growth measurements that we can make from voids. The work I'm going to be talking about with you was recently published, and the archive link is shown on the right of the screen. So if you're still interested after I finish talking, I highly recommend that you go check that paper out. I gave a talk on similar concepts last year, so I'm going to be repeating some of the background information from that, and then we're going to be focusing on new results from the full Sloan Disco Sky survey over the full redshift range that we can measure. When we talk about large-scale structure and results from galaxy surveys, we typically talk about results found through barogarnic acoustic oscillations, or BAO, and galaxy clustering. My goal today is to show you that there is a considerable amount of information that can be gained by looking at voids, and so for the best constraints we should be using BAO, galaxy clustering, and voids as our main pillars of observational cosmology. Using voids we can get even more information out of the galaxy surveys, and I want to emphasize that we're not doing any extra data collection, anything like that. We're just analyzing the existing data in a new way. So essentially we are pulling out this extra information for free, so we definitely should. Potentially this introduces more areas for systematic issues in these results, but we'll talk later about how we quantify these and how we include them in the error budget. With the growing number of tensions in cosmology, so the Hubble tension, the growth rate tension, etc., as many measurements as possible of different parameters is good to help, one, solidify that these tensions are indeed there, and two, help make constraints on different possible theories that could alleviate these tensions. So let's start with the basics of how we do our analysis. What we do is we start with a tracer of the matter field. So in our galaxy surveys, what we use is the luminous red galaxies. You can in principle do this on ELGs, but so far all work has been based on LGs. So in this case, we have these LGs which trace the underlying matter distribution. From this tracer, we construct a density field and search through this density field for underdense regions. We then take these regions and stack them together on top of one another. So each of these regions has a random shape and orientation, but there should be no preferential direction or preferential shape for these. So if we keep stacking them one on top of another, we should end up with an object that is spherical on average, provided that you use enough voids for this. The standard shape for this void stack will get warped by two different effects. Lucky for us, this isn't a nuisance. This is something that we can pull out a lot of information from. So the first effect is redshift-space distortions, or RSDs, so the Doppler shift of a galaxy's peculiar velocity on the measured redshift of a galaxy. If galaxies are all flowing away from a central point, as happens with a void, where galaxies are being pulled from the central underdense region towards the outskirts more dense regions, then this measured shape on the sky will become elongated by these galaxy peculiar velocities. The second effect is the Alcock-Paczynski effect, which is where when you assume a cosmology when converting redshift to distances, you assume a cosmology that is wrong from the truth. And so example of what this would look like is shown on the right. Here on the right, we've assumed a matter content of the universe is lower than the true matter content, which leads to an incorrect measured distance of a galaxy, but this will be incorrect by different amounts for closer galaxies versus further away galaxies, which leads to an anisotropic stretching in this case. Let's talk about the observable that we use in this work. So what we do is we take our void centers and we count the number of galaxies in bins in radius and angle around this void center, and compare the number of galaxies found to that in a random distribution. From this we can create a correlation function which is called the void galaxy correlation function, and perform a change of basis into Legendre multipoles. So we have the monopole, which gives information in the relative direction, and the quadrupole, which gives information about how anisotropic this correlation function is. So you can see this as monopole in blue and the quadrupole in red. We can see from the monopole that we have a less dense region towards the center, increasing as we get more and more as we get more towards our void edges. We have an overdense region at the edges of the void, we expect to find a galaxy, and then this goes back towards zero as we end up outside the void, so we end up expecting the same probability as a random distribution. The quadrupole shows anisotropic stretching, negative in the less dense regions, positive in the overdense regions. So what I'm showing at the top of this slide is the quadrupole at a fixed cosmology. And here we have varied two different parameters. So we've varied S sigma 8, which tells us how fast structures collapse in the universe, and we also have this ratio of the alpha parameters, which we'll get into a second what these are, but basically this tells us how close our cosmology that we assumed is to the truth. You can see that these have two distinct effects on the quadrupole, so we can run joint fits of both parameters in order to measure our constraints and get constraints out for both of these different parameters together. A simplification of our model is shown below. The basics are that we have a redshift-space correlation function, which is our observable. We also have a real space correlation function on the right, without redshift-space distortions or the Alcock-Paczynski effect. So this real space correlation function is something that we measure from our catalogs. To map between the two, we use a Jacobian orthocoordinate transformation shown on the right. Inside the Jacobian, you see this V of R term. This is the radial outflow velocity from a void of the galaxies flowing out from the void, and so this can be calculated using linear theory. So while we have a non-zero density and non-zero velocity profile of these voids, we can map the link between the two using linear theory. S sigma 8, which is one of the parameters we measure, comes from this linear mapping. The ratio of the alpha parameters comes from the redshift-space correlation function, where we assign these alpha parameters to the distance perpendicular and along the line of sight in order to account for the Alcock-Paczynski effect. So again, that's where we may have assumed the wrong cosmology when converting our redshift to distances. A slightly more advanced model, which is what we use in our work, involves convolving this with a probability distribution function for a random line of sight velocity component. Essentially what we're doing here is just adding a dispersion term around this coherent outflow velocity of galaxies flowing away from the center of a void. So just to summarize what we need to be able to do this analysis, we need three input functions, i.e. templates. There is some progress heading towards like a template-free approach, or even just eliminating one or two of these inputs, but that has been tried in this work yet. That is subject to future results. So what we have is this psi of r term, which I've said before comes from approximate marks, and this is approximate marks where we have used RSD removal reconstruction method in order to get an approximation of the real space position of galaxies. We also need a density profile and a velocity dispersion profile, which we take from an n-body simulation that has full dark matter information available, and then galaxies are populated in this n-body box using a Hale occupation distribution that is appropriate to the galaxy survey that we are trying to get results from. So that's enough about our background. Let's start talking about some results from this paper. First, let's just talk about the survey we used. So we used results from the full SDSS survey. SDSS has like 4 different sub-surveys. So we have MGS at low redshift, whose sky footprint is shown in green on this figure. We have low Z, which is shown by this orange color in the top right. We have CMAS, which is shown in this blue color. And then we have eBOSS, which is shown in orange here. And the redshift ranges are as listed in this figure. We split our work that we did into this into 6 redshift bins, so that we are able to build up a consistent picture of our parameters over their evolution in redshift. And what we wanted to do was run all these results through a consistent pipeline across as wide a redshift range as possible, in order to get consistent results, and in order to just get a picture of the evolution of different parameters. To find voids in this, we use the Revolver code, which is available here on GitHub. Revolver has a couple of different void finding algorithms that are available. So in particular, there is Zoboff voids and there is voxel voids. So we use Zoboff void finder, which is a watershed-based void finder. In order to get accurate positions of our voids, we use an RSD removal technique. to estimate the real space galaxy distribution prior to void finding, and then we run void finding on that RSD removed galaxy field. The reason we do that is for two things. One, that this removes selection biases that happen when you find voids in redshift space. So there has been good discussion on this in several papers. In particular, I refer to you on the two here, the first by Nadatha et al. On the left, and the second by Correa et al. On the right. So these both contain very good discussions about why this is necessary and why we can't use voids that are found in real space. This also allows us to to get an estimate of the real space correlation function, which we mentioned before is an input that we need into our theoretical modeling. So we have results in 6 different redshift slices. I'm just showing you results from 2 of these, just to kind of summarize these and show you what they look like. So our measurables are the monopole and the quadrupole. Our best fit theory is shown by the blue line, and then these gray bands is just the best fit theory of 250 approximate marks, just to show that what the results for the data roughly matches what we expected from the marks. So to perform this model fits, we use the Victor code, which is available on the GitHub link shown at the bottom left, and we fit for F sigma 8, alpha purple over alpha parallel, which is the Alcock-Paczynski measurement, as well as 2 other nuisance parameters, and we perform a MC exploration of the posterior. On the right is what the results look like for the 2 main parameters of interest, F sigma 8 and alpha perpendicular over alpha parallel. So you can see that we get these nice contours and nice Gaussian results out for these. Again, I'm only showing 2 out of the 6 redshift slices here, but just to keep so this slide isn't too messy. But the results for the other 4 redshift slices look very similar. Now we have this, we need to worry about our systematic errors. So the way that we tested for this is that we ran our full pipeline on 250 fast approximate marks for each of these redshift slices. And then we found that the best fit parameters for these mark catalogs, and we compare that to the truth value of the cosmological model that's been assumed for these mark catalogs. So difference at the fiducial cosmology is what we call our modeling limitations. So this is difference between the results that we expected to find and result that our model finds. We also rerun our analysis at different cosmologies that's not the truth for these marks. So the truth for these marks was approximately setting omega matter to be 0.308. We also rerun our pipeline assuming that the cosmology was omega matter is 0.28 and omega matter is 0.34. In order to test limitations of assuming this cosmological model. As for the data, we don't know what the truth should be. So these errors are found out through the mark catalogs, and then get added in quadrature to the systematic errors in order to get the total error budget. For this work, the systematics were small. These typically 10 to 15% the size of the statistical error bars. However, this is something that needs to be noted for future work. For upcoming surveys such as Euclid and DESI, these statistical error bars won't necessarily shrink, while the statistical error bars will. And so they'll become more and more dominant in the total error budget. So to put this into some cosmological context and show results for the full redshift range, we first convert our alpha parameters into measurements of dm over dh, which is the ratio of the co-moving angular diameter distance to the Hubble distance. This ratio acts as a test of the geometry of the universe. Left shows these measurements compared with redshift, and for context we have shown similar results from BOSS and eBOSS BAO and galaxy clustering. As well, in blue is results for Planck assuming a flat lambda CDM model. We also have a flat WWA cosmology, where Planck shows a preference towards a more negative W value. So you can see here that we provide better constraints than available without voids in these surveys, and our results show excellent agreement with a flat lambda CDM model, not a model where W and WA are allowed to vary. Also, for context, we show a closed universe with omega m equals to 1, and an open universe with omega lambda equal to 1. On the right, in the top panel, we show the growth rate from this work, compared with Planck, with a flat lambda CDM cosmology in blue. In the middle panel, we compare this to galaxy clustering results. And on the bottom, you see our results compared with other void analyses. So you can see that we have comparable constraints. Galaxy clustering is not quite as tight, but still provide useful extra information as well. To put these results into another context, on here we have fit an open model where we allow omega m and omega lambda to vary and do not assume spatial flatness. So the sum of omega m and omega lambda basically just doesn't have to be equal to 1. We can see that voids provide a very narrow band in this plane, and only assuming that omega matter is greater than 0, i.e. there's some mass in the universe, which seems like a reasonable assumption, we can get an 8.7 sigma detection of dark energy. And that is just from voids alone. You can see this detection, you can see that direction of the void contours are highly complementary to that of the Paczynski supernovae, and SDSS BAO from the same data, as well as Planck. So in the near future, our goal is to combine these results with BAO and galaxy clustering from the same data and get the tightest constraints possible from SDSS. For the eBOSS results, this has already been done. So what we're showing here is just the highest redshift bin of our 6 redshift bins in this paper. And you can see that the contours from BAO and galaxy clustering on the parameters measured are perpendicular to that from voids. So we can get a very large gain information and much tighter constraints when we combined BAO and RSD with voids together. For this eBOSS data bin, this was a 55% reduction in the allowed parameter space. So this is a very large reduction. And again, in the near future, we will be doing the same work for the other 5 SDSS bins in order to get the most accurate constraints possible from this survey. So just a quick summary of what we talked about. We can extract a lot more information from these galaxy surveys, and we can do that for free. These surveys can provide powerful constraints on dark energy and other extended models. Voids combined with BAO and galaxy clustering provide the tightest constraints possible. I hope that I convinced you that voids are going to become a new pillar in observational cosmology and can help provide the tightest constraints on these galaxy surveys. We published these results quite recently, so if you're interested in this work, please check out the archive link shown on the right.